Okay, so this question is asking about the relative acidities of the CH hydrogen or the versus the OH hydrogen. And in order to look at, let's call this H1 and H2. So if we remove H1, or I should say, the best way to predict relative acidities is to look at the conjugate base and compare the two conjugate bases, because it's the relative stability of the conjugate base that is really relevant, the most relevant aspect of predicting relative acidities. So let's look at the conjugate base of removing H1. So if you pull off H1, you have this conjugate base here, where now you have two hydrogens there and a minus charge there. And then here we have our OH here. Okay, doesn't tell us much yet. So we need to look at the other conjugate base. So I'm going to look at, let's pull off this proton, proton number 2. So this is removing proton number 1, and this is removing proton number 2 to make the conjugate base at that position. So here is what we get when we remove H2. We get this anion. And again, really, how do we determine the relative stability of this conjugate base versus this? And we know that the most stable conjugate base corresponds to the most acidic proton. In other words, acidity relates to the ability to lose a proton. And it's going to be easier to lose a proton if the result is more stable than it is to lose a proton where the result is less stable. And so which one of these is more stable? Well, for one thing, you have a negative charge here. The negative charge in this case is on carbon, whereas here the negative charge is on oxygen. And so which one of these atoms is more electronegative? Well, oxygen is farther to the right in the second row than carbon, so it's to the right of carbon, and so it's more electronegative. Therefore, it can handle a negative charge better than carbon. Therefore, a negative charge on oxygen is more stable than a negative charge on carbon. The other question relates to, or a question of relative acidities and the stability of the conjugate base relates to a lot of different things. The element effect is one of them. So O versus, let's put it in the same order here, C versus O. So oxygen is more electronegative. It can handle a negative charge better. We also have a resonance effect. And the question is saying explain using resonance structures. So we can draw a resonance structure here, putting these electrons there and moving those on putting the lone pair into this bond and the pi bond onto oxygen. And we can draw our double-headed arrow. And let me draw that a little bit nicer. Double-headed arrow with the double bond now here and the lone pair on oxygen. We still have our hydrogens and carbons in the same place. We have a resonance structure here. Well, we also can draw resonance in this structure. And if we do that, we move this over, just close that. If we draw that resonance structure, we have CH3, CO. So, does resonance tell us anything about the relative stabilities here? Well, let's look at these resonance structures. Here you have the negative charge on oxygen, and here you have the negative charge on oxygen. So this extra resonance structure, the fact that they both have resonance structures means that they're both more acidic than CH or OH groups that don't have resonance structures. So that's a separate question. In this case, since both of these compounds have one other resonance structure, they can both delocalize their negative charge. This one is delocalized between carbon and oxygen. So this negative charge is delocalized between carbon and oxygen. This negative charge is delocalized between oxygen and oxygen. So the fact that there are resonance structures here doesn't really tell us much about the relative acidities. The main factor determining the relative acidity, again, is the element effect, because in this case you have the negative charge shared between carbon and oxygen, and here it's shared between oxygen and oxygen. And so overall, since carbon is quite a bit less electronegative than oxygen, this is the more acidic proton. H2 is the more acidic proton, leading to the more stable conjugate base.